Hello, this is Nicholas, and I have something kind of interesting planned. I got a linear algebra textbook from one of my teachers, which I've kind of always wanted to study and go through, and I know a little bit of the basics. And so I decided, as I'm going through this linear algebra textbook, I might as well make videos on the sections as I go through them. Making sure if I can explain it to you guys, then I am doing a good enough job in understanding it on my own, and maybe it might help some of you as well. The textbook that I got, and I'll put it in the description, it's called it's Elementary, and whenever they use elementary, it's usually not that elementary. Elementary Linear Algebra, a matrix approach, which is kind of interesting. Normally, matrices are put off until a later chapter, and there's three authors. It's Spence, Insel, and Friedberg. He's probably German. So I wanted to go through probably the first. I'm thinking probably one section per video, but the first three sections are really pretty basic, and they could probably be put into one whole video. So I'm going to go through them with you. So what is linear algebra? Right, that's probably the first question. So linear algebra is almost basically entirely composed of a study of matrices and vectors. And so now the next question is, well, what is a matrix? So a matrix is just an array of numbers, really. Let's say you have the matrix. We write them by their row. They have dimensions. We write them by their row, number of rows, and their number of columns. So let's say, for example, we had an m by n matrix, so m rows and n columns. Then we could write it like this. We write it with parentheses. If we had a 2 by 2 matrix, let's say we have an A, B, C, and D. This is an example of a 2 by 2 matrix, and it's also considered a square matrix because the number of rows equals the number of columns, which is both 2 in this case. And let's say we have another matrix, 1, 2, 3, 4. It's also a 2 by 2 square matrix. We define equality between matrices, and this might seem obvious at first, but it can be really powerful later on. We say two matrices are equal if and only if they have the same dimensions, which is true, they're 2 by 2, both 2 by 2, and each of their corresponding entries are equal. So if we said that ABCD, this matrix here, the first matrix, ABCD, is equal to the second matrix, 1, 2, 3, 4, that would imply that A is equal to 1, B is equal to 2, and so on. And matrix addition is defined pointwise. So what this means is, so let's say I'm adding the matrix EFGH. What I get in this first row, first column here is A plus E, and then I get a B plus F in the second column, C plus G, and D plus H. So that's what we mean by pointwise. We start, if you imagine each entry as a point, we have to use each of the points in the matrix. All right. Now I mentioned matrices. Now what about vectors? The book has an interesting definition of a vector. Normally, when you think first about vectors, maybe you learn this in a pre-calc class, or maybe you take physics or something, and you see them treated as like arrows, where we have a tail and a head here. in linear algebra, we define a vector actually to be an n by 1 or 1 by n matrix. So, for example, the matrix, and this is also a vector, 1, 2, that's a vector. We could also write it as 1, 2. It doesn't matter which way. I prefer this way. And we define... See, a lot of times we're interested in generalizing our results in linear algebra, and so we need a generalized space to take those results in. So we define an n-dimensional space, R, and then it looks like an exponent n, r to the n, to be the set of all vectors with n components. So what does that mean? Well, let me write it. This is really what's defining of any space. This actually, and this is good, it gets us into another idea. If we write, normally are used to seeing this circled vector here written in maybe this form, or maybe you've seen it as 1i hat plus 2j hat. I and j being your standard basis vectors in the x and y direction. In other words, I'll write them in red. In other words, we go 1 unit here, and we go 1 unit here, and this is I hat, and this is j hat. So what this is getting into now is the idea that an n-dimensional space has n basis vectors. Or in other words, in n-dimensional space, you can have n lines all perpendicular to each other. That's really, if you sit down and think about it, that's kind of mind-boggling, right? I'm going to do my best here to draw 3 dimensions. So that's 3 dimensions, and, this x-axis here is like, oops, I still have the, this x-axis, y-axis, and then the z-axis, they're all perpendicular, and you would imagine the x-axis kind of coming out at you, the y-axis going left and right, and the z-axis going up and down. You can't really use left, right, up, and down, but, I'm using it for the sake of simplicity here. All 3 of these lines, right angle, this is a right angle, and this is a right angle. They're all perpendicular to each other. They all meet at 90-degree angles. And beyond this, we can't really fathom 4 lines all perpendicular to each other, right? We only live in a 3-dimensional world. But we can still consider results in space higher than 3 dimensions. So what I wrote here, it gets us into the idea of what's called a linear combination. And so we say that a vector v is a linear combination of the set of vectors, say, u sub 1, u sub 2, up to u sub k, if vector v can be written in the form... Oh, and also we define the set c sub 1, comma, c sub 2, comma, comma, c sub n to be a set of n scalars. So numbers that scale the vector by some amount. If, for example, I started with I hat and I turned it into 2I hat, then the magnitude of I hat has been increased or scaled by a factor of 2. That's why we call them scalars. They scale space, they scale vectors. They're just numbers that you're normally used to. So V is a linear combination of the vector set u sub 1 up to u sub k if it can be expressed in the form c sub 1 u sub 1 plus c sub 2 u sub 2 plus dot 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 plus c sub k u sub k. And so where does the name linear combination come from? It's kind of intuitive. First of all, the combination part, right? You're summing, you're taking combinations from these two sets here. And the linear part comes from the fact that all of these vectors are, you can't really raise vectors to a power, so to say, but, you know, these vectors are, they create the shape of a line, right? The vectors aren't, you know, curved in any way. They are straight. They make a line. That's where the linear comes from. And when I meant up here with the 1, 2 being expressed as a linear combination of I hat and j hat, another way you might think of this is that if I were to just get rid of this j hat here and just consider the I hat, and let's say I had c I hat for some arbitrary scalar c, then as I were to change c from the set negative infinity to infinity, you know, in other words, if I were to make c, you go from 1,000,000 to minus 1,000,000, then what I would get is I would trace out a line here, right? I hat would be shifted. And so I would get a line traced out along the x-axis. So whichever way you'd like to think of it, those are two motivations for where the word linear comes from in a linear combination. Another thing the book mentions here is, they mention matrix subtraction. It's exactly the same as matrix addition, except everywhere where you have a plus sign, you change it to a minus sign. It's also defined pointwise. They mention, and I guess this is important to know, it should be expected based on how we define matrix addition and subtraction, that it is commutative. So in other words, A plus B, a matrix A plus a matrix B, is the same thing as a matrix B plus a matrix A. It is also associative. So what does that mean? It means if I have matrix A plus a matrix B, if I were to take those first, add them together, and then add the matrix C to that sum here, it's the exact same thing as taking the matrix A and then taking the sum B plus C, finding that first, and then adding it to A. They are the same thing. Now the book mentions what's called the transpose matrix, which is denoted as A, and then it's got an exponent of t there. And so in a transposition matrix or a transpose matrix, what happens is every row becomes a column, and every column becomes a row. So, for example, if I have the matrix A, B, C, D, and let's call that matrix A, then the transposition matrix is A, B, C, D. This row here now became a column here, and this row now became a column here. Another way you can think of transposition is, let's say we have the original matrix. You can see how the transposition matrix is symmetric about this line here that I've drawn. And so what we can do is we can just flip, we reflect along this line, and that's another way to, it's not as rigorous, but it's another way to generate the transposition matrix. And if we were to take, it should make sense for to take the transpose matrix and then transpose that matrix, we get the original matrix. And of course, if we were to multiply by some scalar s to that matrix and then take the transpose of that, that's the same thing as taking s and then multiplying by first taking the transpose of the original matrix. And let's say, again, let's use another example here. They mentioned submatrices. The idea here is also really pretty intuitive. Say I have this matrix, then a submatrix it is just a matrix obtained by considering any specific rows or columns. And of course, any matrix is its own submatrix. But for example, we could say we ignore this first row there, then a submatrix of our original matrix could be the matrix D, E, F, G, H, I. That would be a valid submatrix. Or we could ignore this, and then we could ignore those two columns. I mean, and we could just get the lame matrix G. Not all that interesting, but it is technically a submatrix. They mention vector addition in here. Vector addition is really very, very easy. It's because a vector is just a matrix with either one row or one column, and since we have defined matrix addition, then we have just as easily defined vector addition. So, for example, if I were to add the vectors 1, 2, and the vectors 3, 4, then I would get the vector 1 plus 3, 2 plus 4, or the vector 4, 6. Yeah. They mention oh wow, that's cool. They mention a geometric interpretation of vector addition, and I will show that here. I personally don't think of it this way, but I mean, if it works for you, it works for you. So let's say that, well, okay, let me draw a good diagram here. Let's say we have the vector 1, 2 and the vector 2, 1. So that would, let's call this vector v, and let's call this vector w. Then vector v would look like that, and vector w would look like that. The way I always think, and it always works, in my mind nicely, is just break them up into components, right? So, and that's what is nice about this form here, is that it tells you the component magnitude right away just by looking at it. So, break them up into components here, right? We have one, we have just I hat really along the x-axis of vector v, right? An x component of magnitude 1 and an x component of magnitude 2 on w. So our resultant x component, when we add the vectors, will have a magnitude of 3. And likewise, it will have a magnitude of 3. Oh, I want to make this good. Along the y-axis. And so our resultant vector will look like this. I think that's good enough there, really, for vector addition. Let's see. Talked about linear combinations. Oh, let's actually see, if I give you some arbitrary vectors, can we determine if they're a linear combination of some other vectors, some other set of vectors? So maybe we have the vector 4, negative 1. And we want to know, is it a linear combination of 2, 3, and the vector 2, 3, and the vector 3, 1. If it were a linear combination of the vector 2, 3 and the vector 3, 1, then the vector 4, 1 could be written in the form x, where x is a scalar, times the vector 2, 3, plus y is another scalar, times the vector 3, 1, which, using matrix addition, is the vector 2x plus 3y and 3x plus y. As I said before, and it will now be used here, two matrices are equal if and only if they have the same dimensions and their corresponding entries are equal. So if these are equal, that would imply that we get 4 is equal to 2x plus 3y, and 1 is equal to 3x plus y. It's now a matter of just solving this system of equations. So what I'm going to do is multiply the second one by 3 and subtract them. So I get 1 is equal to 2x minus 9x. It's minus 7x. And then the y's cancel out. So x would be negative a seventh. Yeah. Oh, I subtracted them. Whoopsies. Oh my gosh. Here, I'll just write it out. So what happens? 4 is equal to 2x plus 3y. And 3 is equal to 9x plus 3y. Subtract the 2. Oh no, I had it right. 1 is equal to negative 7x. So x is equal to negative 1/7. And that would mean that 1 is equal to negative 3/7 plus y, or y is equal to, this is 7 over 7, so y would be 10/7. So yes, the vector 4, 1 can be expressed as a linear combination of the vector 2, 3 and the vector 3, 1, and namely that linear combination would be negative 1/7 times the vector 2, 3 plus 10/7 times the vector 3, 1. Now, by Euclid's postulates, we know, well, first, before that, we know that this is an equation of a line. This is an equation of a line. If two lines intersect by Euclid's postulates, then the intersection of the two lines creates a single point. In Euclidean geometry, at least. In other geometries, that's not the case, but in Euclidean geometry, which is what we deal with in linear algebra, that is the case. So what this means is that any equation of the form ax plus by equals c and dx plus ey is equal to f will, if it has a solution, it will have exactly one solution by the geometry of the equations. And likewise, if, say, we had an equation ax plus by plus cz is equal to d and what letters now? EF. Ex plus what? A, B, C, D, E, F. Fy E, F, G, Z is equal to H, and A, B, C, D, E, F, G, H, I, J, K, L, Z, Y, X, and we're going to add them, and that's an L, not a 1. These are all, X plus BY plus CZ equals D. Those are planar equations. They are equations of a plane. And so how do I know that these are equations of a plane? Well, imagine if I were to keep z as a constant. In other words, I drew it up here somewhere. along this z-axis here, say we're staying right here at this level, and we're only moving along the x-axis or along the y-axis, but our z-axis is not changing, then we would get the equation of a line, right? If we were then to change z, we would have the line, and it would, it's kind of hard to, I would recommend watching 3 Blue 1 Brown. He has a really good animation of this. But the line would then sweep through the z-axis, and it would create a plane. It would sweep above, it would go up and down like this. And so it would create a plane. We have a line here, and then if it moves up and down, then it creates a whole plane, right? So that's an intuition, at least, as to why those are planar equations. Now, these are 3 planes. The intersection of these planes will create 3 lines, because the intersection of 2 planes creates a line. Another one of Euclid's 5 postulates. And the intersection of these 3 lines will create, it'll create 3 points, but it'll create 1 point on which they all intersect, again, by Euclid's postulates, which are true. So what I'm getting at is the fact that any linear system, any system where the scalars, where we have scalars and then everything is of degree 1, that's why it's linear. Every linear system of equations has either no solution, it would have exactly, and I put emphasis on exactly, 1 solution, or infinite solutions. And that is my point in getting at using the geometry of the equations. I think gives a good intuition as to why that is true. Let's see, what else? This is another important. I mentioned before the idea of the linear combination, and I gave the example of the vector, well, I wrote it as 1, 2, which is 1 times I hat plus 2 times j hat, so it's a linear combination in I hat and j hat. Maybe the question pops into your mind, maybe it didn't, it popped into mine. The question is, what if we don't use I hat and j hat as our basis vectors in 2 dimensions in R2? What if we were, say, to define new basis vectors, maybe call them I star, to be 2 I hat plus 1, and j star to be 3 j hat plus 2. So in other words, now we would be expressing vectors in the 2-dimensional Cartesian plane based on the basis vectors that would now look something like this. We would have that would be I star, and j star, 1, 2, it would be going something like that. So the question is, are we still able to express every vector in R2 in 2 dimensions using these new basis vectors? And there is a lot more detail into this when you get into the topics of eigenvalues and eigenvectors, which are solutions to the equation ax is equal to lambda x, where we get the change of basis vectors. But the truth is that yes, if these two new vectors, I star and j star, are non-parallel vectors in 2 dimensions, and the emphasis is put on non-parallel, because if they were parallel, then, say maybe j star was instead twice of I star, then you'd only be able to describe vectors along this line here. But if they're not parallel, then it is true that every vector in this 2-dimensional space, or in any n-dimensional space, is a linear combination of, in this case, I star and j star. It seems intuitively true to me why this would be the case, but I encourage you to think about it if it's not intuitively true to you. If it's not intuitively true to you, ask yourself, well, why not? I mean, what vectors couldn't you express if you chose 2 different basis vectors that were non-parallel? What types of vectors could you not express? And I then encourage you to explore those possibilities for maybe the vectors you thought you couldn't express, and see why you can indeed express them. And you could use the algebra that happened right here to show that you can in fact express the vectors that maybe you thought couldn't be expressed as a linear combination of your new basis vectors. So yes, any non-parallel vectors if this were our n dimensions, we would have n basis vectors. No matter what those basis vectors are, as long as they are all non-parallel to one another, any vector in that n-dimensional space can be expressed as a linear combination of those n basis vectors. That's a pretty cool fact, isn't it? There's another matrix that they mention here that is awfully important, and it comes up a lot in linear algebra. It is the n-dimensional, what we call the identity matrix. And we define the identity matrix to be, it's a square matrix, so it's n by n, and the columns are the standard basis vectors in our n. So in other words, the vector 1, 0, ... 0, the vector 0, 1, ... 0, and the vector 0, 0, ... 1, where there's n entries in here, and as in here and here. So what would this look like? Maybe the 2-dimensional identity matrix, we would denote it as I sub 2. It would just be the matrix 1, 0, 0, 1. Or I sub 3 would look like 1, 1, 1, 0, 0, 0, 0, 0, 0. So it's a matrix with 1 along its main diagonal there, and then everywhere else is zeros, as you would expect since it's composed of the standard basis vectors. And why do we call this the identity matrix? We call it the identity matrix. Well, let's go back to, not even thinking about matrices, but, normal numbers here. Let's say we have the number 7, and we're looking for some number, call it x, and x is what we call the multiplicative identity. So that 7 times this multiplicative identity gives us our original number that we started with 7. So any number a times the multiplicative identity gives us a by the definition of a multiplicative identity. Well, what would x be here? Obviously divide by 7, and x would give you a 1. So 1 is the multiplicative identity. In other words, 1 times any number gives you that original number. In the same way, and we'll later go on to define matrix multiplication, if I take, say, the vector, or the matrix, the identity matrix in 2 dimensions, namely 1, 1, 0, 0, and I multiply it by any 2-dimensional, with 2 rows and 2 columns, matrix, say A, B, C, and D, then I will get the matrix A, B, C, D. That's the most useful property of the identity matrix. The book goes on to define one other, it's really more of a derivation of one other special matrix, which is called the rotational matrix. And what the rotational matrix does is it takes a point. So, maybe we have a point here on the head of this vector, and we start at an angle theta here from the origin, and then we rotate this point on the head of the vector, and let's say it was originally xy, by some other angle phi, so that we get a new point x prime comma y prime on the tip of this same vector. And we want to find what x prime and y prime would be. So it's useful to work in polar here, right? Because this drawing has radial symmetry, right? It's symmetric about this common radius because that is, I still have the thing on, because that is what a rotation does, is it rotates, creates a circle about some fixed point, which is, in this case, the origin. So it would make sense to use polar here. So x would be r cosine theta, this being r, and y would be r sine theta, and after the transformation, x would be r cosine of theta, our original angle, plus the angle we rotate by, phi, which is r cosine theta cosine phi, minus r sine theta sine phi. And likewise, and this is x prime, whoopsies, because that's the new point after we rotate. Y prime would be r sine of theta plus phi, which is r sine theta cosine phi plus r cosine theta sine phi. We could simplify this some more because x prime is really just, this part right here is x cosine phi, and this part here is y, so minus y sine phi, and y prime likewise is y cosine phi plus x sine phi. I'm going to change the order of y just so my x's are in line with my x's and make it x sine phi plus y cosine phi. Since addition is commutative, it forms an abelian group. Okay. So if we were to interpret this as a matrix equation, then the matrix equation we would get is that the matrix x prime y prime is equal to the matrix, and this is why I had my x's with my x's and my y's with my y's, because now I can just look at their coefficients here. So I get the matrix cosine cosine what? Cosine phi, negative sine phi, sine phi, and cosine phi times x, y. And this matrix here is the two-dimensional rotational matrix. So it tells us if we have a point xy, which we can really treat as a position vector or a vector with its tail at the origin, then we take the coordinates of the head of the vector, which, maybe they're 2, 1, and maybe we want to rotate this, maybe it's at an initial angle theta, and we want to rotate it by 30 degrees, say, then we would plug in 30 degrees wherever we see phi, and we would get root 3 over 2, negative a half, and root 3 over 2 times the vector 2, 1, and we would do that multiplication, so we would get 2 we would get 2 times root 3 over 2 and a half plus 1 times negative a half and root 3 over 2. And so we would just get root 3 over 2, 1, plus negative a half root 3 over 2, which is the head of the vector would lie on the point 1 minus root 3 over 2 and 1 plus root 3 over 2. And that's an example of using the rotational matrix. And so what happened in this step here is what's called the matrix vector product. And I think it's kind of a misnomer because a vector is a matrix, so you could kind of call it the matrix product. But this matrix here with only one column is more specifically called a vector. And so it's the matrix vector product is the linear combination of the columns of this original vector, so this and this, with the coefficients of the vector, so this and this. So that's exactly what I did here. I took this coefficient, this scalar, multiplied by this row, or column, sorry, and then took this scalar, the 1, and multiplied by that row. And I created, because this is the form of a linear combination, I created a linear combination. And that's what we define the matrix vector product to be. There's just a couple more things I wanted to mention, and then I'll be done. I mentioned that before a linear system of equations can have only exactly one solution, infinitely many solutions, or no solutions. We give names to these. If we say that the linear system is consistent, if it has one or more, so one or infinitely many solutions, and we say it's inconsistent otherwise, so in other words, it has no solutions, the system would be considered inconsistent. Now, there are some row operations that we can do on matrices. So let's consider the system of linear equations x sub 1 minus 2x sub 2 minus x sub 3 is equal to 3, 3x sub 1 minus 6x sub 2 minus 5x sub 3 is equal to 3. And lastly, 2x sub 1 minus x sub 2 plus x sub 3 is equal to 0. We consider this a square system of linear equations because the number of variables, or the number of unknowns, is equal to the number of rows of the system. If we were to, it turns out we can represent this system as a matrix, and this is one of the most important applications of matrices, is solving linear equations. And so, yes, I'm home. And so we can write this system as the following matrix, and it'll tell us everything we want to know. So if you have 1, -2, -1, 3, and I'm going to put a little bar here, just because this bar separates the coefficients from what they're actually equal to on this side. This would be a 3, this would be a 0, -5, -6, 3, 2, -1, and 1. And we call this matrix, the whole thing, we call it the augmented matrix of our original system. And as you can see, it tells us everything that we would want to know about the system, written in a much more compact form. We call this part of the matrix to the left of the bar that I've drawn the coefficient matrix, which makes sense, the coefficient matrix. And we call this part to the right of the bar the constant matrix. And it should also make sense. It's what the things are equal to, the constants on the right-hand side. And so since, you learn this in Algebra 1, what we can do to this systems of linear equations here is, well, there's a number of things, right? First of all, we could flip-flop any row of the linear equation. So we could write, if this is equation 2, 1, and 3, we could flip we could put equation 2 where equation 1 is and put equation 1 where equation 2 is. It doesn't matter the order in which we write them in. We could write it as 3x sub 1 minus 6x sub 2 minus 5x sub 3 is equal to 3, and then write x sub 1 minus 2x sub 2 minus x sub 3 is equal to 3. It doesn't matter which way we write them. Since these equations, in this case, represent planes, we can always multiply a plane by a scalar. That scalar, I'm going to try to keep it a little neat. That scalar will not change the solutions that the system gives, right? It's just a scalar multiple of what we already have. So the plane will just increase in magnitude. It won't change in the solutions that it gives. So we can multiply any of the rows of this by some constant c, where, of course, c cannot be equal to 0, because if we multiply by 0, then we would just get everything. It would just get 0 equals 0 for every row. So any non-zero constant we can multiply by. The other thing you were taught is, and this is mainly used in the method of elimination, is that we can combine. What we could do is say we in these first two equations here, say we wanted to get rid of x sub 1 here. We wanted to eliminate x sub 1 here and here. How could we do that? Well, what we could do is what I said earlier. We could first multiply equation 1 by 3, so that the coefficients of x sub 1 were matching. And then we could say subtract, I'm going to say we could subtract 1 from 2, or we could subtract 2 from 1. Either way, whichever way you subtract those equations, the x1 variable of those equations will now be eliminated. Since this matrix represents a system of linear equations, we can do the exact same things to the matrix as we could to the systems of equations. And we call those operations that I just said before, we call them elementary, because they're really pretty basic, row operations. And so there's three that are commonly stated in the textbooks. We can interchange rows. That was the first one I said. We can multiply rows by some constant c not equal to 0. And we can add or technically subtract if we were to multiply by negative c in rule number 2. One row of a matrix to another. That just ties into the idea that I said before with the method of elimination that you were taught in Algebra 1. So, for example, let's say, let me see if I can just get rid of all the stuff I've written here and just move this matrix over some. So let's, isn't that cool how I can just do that? So let's say we want to make this 3 here, we want to make it a 0. What we can do, and I'll write an arrow, is we can take, this is, by the way, we call these row sub 1, row sub 2, and row sub 3. So the first row, the second row, and the third row. We could take, well, we could have row sub 2 go to 3 row sub 1 minus row sub 2. So what we would do is we would multiply row sub 1 by 3 so that the row would now turn into 3 negative 6, negative 3, and 9. And now we could subtract the 2, right? We could subtract row sub 2 from row sub 1. So the first row is staying the same, 3, negative 6, negative 3, and the 9 here. The second row is the one, oh, well, the third row is staying the same too, right? Let's write that in. And now the second row, so we do, I wanted to get rid of that. So we already multiplied by 3, so we take this number and we subtract it from this number. And that's going to go here, so we have a 0. We take this number, we take this number because it's on row sub 1, we subtract it from this number. Negative 6 minus negative 6 is 0. And we take this number and we subtract it from this number. Negative 3 minus negative 5 is a positive 2. We take this number and we subtract it from this number and we get a 6. So that's what the new row would look like. And we could do a number of different things to this matrix, this augmented matrix here. There are a couple of useful forms that we can get the matrix into for solving systems of linear equations. So, for example, there's two different forms here that are nice for us. There's what's called row echelon form and reduced row echelon form. Reduced row echelon form is what's nicest here, and later when I talk about Gaussian elimination, it will come up quite a lot. So I'll first show what well, first I'll show what row echelon form looks like. What it looks like is, so say we've got a matrix. Technically I should be doing parentheses here, whoops. Let's say we've got 1, 1, 1, maybe a 1 there, I don't know. It doesn't really matter where the 1s are so much. And they form this little staircase pattern here. What we demand in row echelon form is that wherever we see a 1, and the 1s have to form this sort of staircase pattern here. In other words, it can't look like, say we had 1 and then 1, 1, 1. This is reversed. It's got to form that downward staircase pattern. 1, 1, 1, 1, 1. And we have this pattern here. What we demand in row echelon form is that the matrix, wherever we see a 1, then there are zeros below every 1 up until the last row. And we don't care what's above, so I'll just put stars. It doesn't really matter. We don't care what's above, but we demand that what's below the 1s is all zeros. This is row echelon form. So what's the difference between that and reduced row echelon form? In reduced row echelon form, we demand that wherever we see a 1, there are zeros all the way down below the 1 and all the way up above the 1. So the reduced row echelon form for the original matrix would look like that. And there's a theorem that I will later prove that I'll abbreviate as reduced row echelon form RREF is unique. In other words, there is only one way to start with a augmented matrix, a matrix that represents this system of linear equations, and transform it into reduced row echelon form. There's only one way to do it, and I'll prove that later on. When I talk later in the next video about Gaussian elimination, reduced row echelon form will come in a lot. It'll help us a lot. And one final thing I want to mention is in this matrix here, let's say I change this to a 0 instead of a 2. What does this mean for the system? Well, later when we get to elimination, well, what this would imply for the system is that it would imply that 0x sub 1 plus 0x sub 2 plus 0x sub 3 is equal to 6. Or in other words, that 0 is equal to 6. Obviously, that is wrong. That's not true. So whenever you see a row and its only non-zero entry is in the final column, then the system is inconsistent and it has no solutions. That, you know, if you were to see that in the traditional way of eliminating and going about simplifying systems of linear equations, that would be obvious to you, but just pointing that out when we are dealing with linear systems in a matrix form. I think that is all I wanted to talk about today. I hope this is somewhat interesting to you. This is really just a lot of the basics of linear algebra, so it's probably not all that interesting. But I mean, you need the matrix. Thinking the matrix. You need the basics in order to move on. If you have any questions about any of these, I would love to answer you, and I will, if someone asks, I will include some of the practice problems from the book if you'd like to work through them. And